Hi, my name is Michael Treidel, and this is my presentation on quantifying the central limit theorem. So here is the agenda for this presentation. First, we will review the central limit theorem so that we're all on the same page. Second, I will talk about a way that we can quantify the similarities between two distributions. Third, I will talk about how this relates to the Berry-Esseen theorem. Fourth, I will talk about how I performed numerical calculations of the Kolmogorov distance. And then lastly, I'll make a few concluding remarks. Recall that the central limit theorem basically states that the cumulative distribution function for a normalized sample mean converges to a standard normal cumulative distribution function as the sample size gets really big. Just to demonstrate intuitively what is going on, suppose our population distribution is exponential, and we are drawing samples from it. We see on the left that for a single exponential sample, the normal and exponential PDFs look quite different. However, for a sample size of 5, we see that the sample mean of the exponential data is starting to look more symmetrical. Fast forward almost 100 samples, on the right we see that there is barely any difference between the exponential sample mean PDF and a normal PDF when the sample size is 100. The central limit theorem is an amazing result, often considered one of the crown jewels of statistical theory. However, there are some serious limitations that affect how practical it is. Probably the biggest problem is that we don't have any idea of how quickly the sample mean converges. For practical purposes, you might ask, does it take 10 samples, or does it take over 100? We will see that it depends on certain aspects of the population distribution. This ends up leading to another question. How do we measure how similar two distributions are? There are many approaches here, but for the rest of the presentation, I'll be focusing on the Kolmogorov distance. Suppose we have two random variables, x1 and x2. The Kolmogorov distance is the greatest absolute vertical distance between two CDF curves. The distance must be inside the interval 0 to 1. This can also be interpreted as the greatest absolute difference in the left tail probability over all values on the real line. If the Kolmogorov distance between two random variables is small, that would mean that the CDF curve values are very similar. If the Kolmogorov distance between two random variables is large, that would suggest that there are big deviations between the two distributions. So going back to our original example with the exponential data, we can now quantify how similar the exponential sample mean is with the normal distribution. For a sample size of 1, we see the greatest difference in right-tailed probability is about 0.16. For a sample size of 100, the greatest difference in right-tailed probability is a little over 0.01. Talking about Kolmogorov distances leads to the Berry-Esseen theorem, which can be thought of as an extension of the central limit theorem. Other than the standard CLT requirements, the Berry-Esseen theorem requires that the population distribution has a finite third absolute moment, which oftentimes tends to be true for lots of distributions. The Berry-Esseen theorem provides an upper bound for the Kolmogorov distance between the normalized sample mean and the standard normal distribution. This provides a quick way to study the convergence of the sample mean for various population distributions. So once again, we will assume the data is coming from an exponential distribution. It can be shown that the Berry-Esseen bound for an exponential sample is approximately 3 over the square root of n. Trying this out for a sample size of 1, the Berry-Esseen bound is around 3. For a sample size of 100, the Berry-Esseen bound is around 0.03. We see that the Berry-Esseen theorem heavily overestimates what the Kolmogorov distance for various sample sizes is. So in practice, one would need to calculate the Kolmogorov distances directly if the sample sizes are relatively small. To calculate the Kolmogorov distances directly between the normalized sample mean and the standard normal, one needs to find the maximum absolute difference in CDFs. A lot of sample means from popular distributions are oftentimes rescaled versions of other common distributions. To make the analysis simpler, it is often more convenient to work with sums of random variables. The Kolmogorov distance is invariant to scale and location changes in both distributions. Thus, the following formula can be used to calculate the desired Kolmogorov distances. So, working with Poisson data, here is a graph of the Kolmogorov distances between a Poisson normalized sample mean and the standard normal distribution. The x-axis of this graph is the rate parameter times the sample size. So, we see as lambda times n gets bigger, the Kolmogorov distance between the sample mean and the normal approximation approaches 0. Now suppose we are working with an exponential sample. We are pretty much seeing the same thing we saw with the Poisson data. However, there is something important to point out. Notice that the rate parameter does not appear in the graph. While the Kolmogorov distance might seem parameter dependent, the central limit theorem ensures otherwise, because the rate parameter is merely the reciprocal of the scale parameter and does not alter the fundamental shape of the exponential distribution. Its influence disappears once we normalize the sample mean. Thus, under the central limit theorem, the Kolmogorov distance between the normal approximation and the scaled exponential sample mean remains unaffected by changes in lambda. The last population distribution I'm going to be considering is data generated by a Bernoulli distribution. Notice that the Kolmogorov distance between the normalized Bernoulli sample mean and standard normal is affected by what the value of the parameter p is. Thus, when looking at the behavior of the sample mean, we need to look at multiple graphs. Here is the first one where the sample size is 5. Notice that the graph isn't smooth nor symmetrical, and the probability values in a neighborhood near 0 and 1 have considerably higher Kolmogorov distances than everywhere else on the graph. Here are the Kolmogorov distances when the sample sizes are 20 and 100. The curves are starting to look smoother, but the lack of symmetry around 0.5 is surprising and requires further investigation. So finally, I just want to mention, that finding the Kolmogorov distances can be done in the same fashion as I did earlier for common distributions. For instance, the geometric, gamma, and uniform distributions can be looked at using the same approach. For more specialized distributions that don't have nice sampling distributions, for sums, another approach could be to use simulation and calculate the Kolmogorov distances using the empirical CDFs. Thank you, and that's the end of my presentation. Thank you all for listening.